do this in English. Then the recording is a little bit more interesting when it's on the internet. So, good morning, everyone. Welcome to my early bird presentation. My name is Tom Eugelink. I'm the software architect for training and simulation at Thales. And Thales is a company that sells radar and optical systems for Navy ships. It's located at the eastern border, near Germany. And in my task as training and simulation architect, I came across a library that I didn't know. I've been doing software development for 40 years, and I never heard of it. And it was actually a quite interesting technology, open standard, open source, and I figured it might be interesting to other people to know about it as well. So that is why I decided to have this small talk. But in order to explain what the library does, it is good to first introduce you to the domain, and when I've explained how we use it, then you can maybe mirror it if it's something that can be interesting to you as well. So I'm going to start with introducing our domain and then talk about the technology, the standard, the library. And for that, I will introduce you to the F-126, which is the to-be newest addition to the German Navy. In about 4 or 5 years, we hope that the first ship will sail. But just with everything in the military, that's always interesting to see if we can get to that mark. The name F-126 is because the previous ship was called the F-125, and the one before that, the F-124. So you've got no idea what kind of ship it is, except that the F is a frigate class. But the project name is a little bit more insightful. It's called the MKS 180. And MKS stands for Mehrzweck-Kampfschiff, multi-purpose fighting ship, warship. And this project was granted to Damen Shipyards, a Dutch company, in 2020. It was on the news, big project for them. And Damen will build this big iron bathtub. It will put it into the water, and then we have a ship. But that doesn't make it a warship. In order to make it a warship, all kinds of subsystems are attached to it. And in this case, for the F-126, to give you an impression, it has 3 guns, 3 types of guns. There is the big one, relatively on the bow, on the front of the ship. It fires 127 millimeter thick ammunition. And there are smaller guns, 27 millimeter, 12.7, on the sides usually to defend the ship. It also has missile systems, which are often the main way of attacking or defending. It has three types. There's 1 offensive and 3 are defensive to protect the ship from incoming air threats. It also has multiple radar systems. The one on the right is the most familiar. It's the navigation radar, which turns around and is used to navigate in the near vicinity. The other 2 are the Navy radar systems, and we used to think that the radar systems are a big turning dishes, but nowadays they are static. They are plates on the side of the tower, so you don't see the typical dome anymore in the profile of the ship, but it has flat surfaces, and then the squares on the side, usually are a little bit bigger, are the actual radar systems. So they don't turn anymore. The ship also has camera systems. The one on the left, there are multiple instances of those present, is used for 360 degrees surveillance to see what's in the vicinity. Infrared, normal camera. And the one on the right is for tracking something that moves about in the near vicinity. It can follow a visual target automatically. And there are other systems, like, for example, the one on the right here is a very big loudspeaker. In order not to always have to use lethal force, you can deter small boats, skiffs away from the ship, pirates. The one in the middle is countermeasurements. It can fire chaffs or flare in the air to defend against incoming missiles. And the one on the left is for electronic counter warfare, detecting or jamming things. And this big iron bathtub with all these systems on it is the warship. But they can't operate independently. They have to be coordinated. You have to use the radar to see things and then react and respond to it with the countermeasures or fire at something. And this whole interaction is controlled from a room, which is not a bridge, as one would expect. The bridge is used to steer the ship, but not to do the warfare tasks. It's done by people in the CIC, Combat Information Center. I'm going to call that the command center from now on to stop using all kinds of abbreviations. And that's usually located beneath the bridge. It's a closed room, doesn't have windows, isolated. And there are a number of people there doing their job. The Germans, being Germans, they built this ship very sturdy, so everything is made redundant, cabling is redundant, and there is also a second CIC or command center somewhere near the rear. I'm not sure exactly where. And the command center has people doing the actual warfare activities of the ship. And it looks something like this. Kind of like what you also see in space travel. There are a number of workstations, or MOCs as we call them, but I'll call them workstations. And there the different people sit, and they have a display for themselves and a status display higher up for the commander who sits in the back to keep an overview of what's going on. And such a workstation looks like this. It has a big screen, a keyboard, a joystick, trackball, mouse, depending on what the client prefers. And on the left side, there are a number of function keys, with the one on top with a little plastic cap. And usually, if you press one of those, then something bad happens in the world. Now, these stations are interchangeable. You can sit anywhere and then set the appropriate functionality for what you want, so they don't have a specific task. And then multiple people do their job. And I've got a small movie for you. To give you an impression of how that interaction goes, how that works. And in this movie, the ship is under an attack, and it will try to defend itself from the incoming aggressor. And I've got no sound.
Ops, this is a UAV, a flash.
Yes, Ops, coming over.
multiple small tracks close to Tango Mai. Possible privateers.
This is up, Roger.
Roger. Ops, this is surveys, flash. Multiple privateers incoming, a swarm.
Roger, incoming swarm. All suspects now hostile. Report when in warning, green zone over.
Hostile in green zone over.
Roger, issue warnings.
Ops, this is air. New tracks from the north incoming. 2776, position 010, tracking south, investigating.
This is Ops, outside airline.
No squawk, no suspect.
Ops, this is air, flash, suspect tracks, descending quickly.
Hostile reacting to warning, breaking off attack profile, turning away, status back to yellow.
Guns, this is Ops. Swarm past the green zone. Now yellow. Engage with guns and Mirador when entering the red zone.
This is guns, roger. Engaging track with guns. Stand by firing. 3 grenades. Fire. Stand by impact.
Stand by.
Target destroyed.
Okay, well, that was some Oscar-worthy acting. But it does give you an impression of the interaction and the cooperation that goes on in the command center. So we saw a number of roles coming by. We heard something of a Mirador being used, and there was a radar operator that was reporting that the track was coming down. We of course saw the gun being operated, and we also had a situation where there was a discussion on how to approach a certain situation. But what's important to understand is that these people are dealing with information. They're really under threat in a normal situation, and they have to make life and death decisions. If they decide not to engage, then they're at stake. If they decide to engage, then they may be at fault. So this process of cooperation and interacting, how the decision is made, needs to be a second nature to them. So they can focus on the decision that's actually being made and not on the process that they have to follow in order to come to the decision. And the only way to achieve that level of comfort in the process is to train it many times over, again and again. And this training is the core functionality for which the library that we're talking about will be used. Seamless teamwork is the basis for making sure that no mistakes happen. Now, the people in the command center, they see the world not through a window. The command center is closed, there are no windows on it at all. They see the world through an application. That's something that also is developed by Thales. And it contains all the information that the subsystems that are bolted onto the ship provide. On the right side, we have a radar view of the vicinity. All the radars available on the ship are merged into one display. On the left, we have some status information. And if the people in the command center want to look outside, then they do that through the cameras that are available. They never look outside through a real window. So if you look at this setup from a structural perspective, from an architecture perspective, then you have this software, Tacticos it's called, on the side. People are working with it, and it is connected through a network with the subsystems on the ship. They provide data, Tacticos sends data, and that way the operators can see what they need to do. The subsystems look in the real world, and they see what's going on. They see the other ships, they see the other planes that fly in the vicinity. If we would park that ship in a harbor and then start training, when these systems are live, then we would have a problem. If you turn on the radar in the harbor, you will fry the people in the building around you. The radar can see thousands of kilometers. It's a powerful system. You can't turn it on in a harbor. Also, when you start training and you have this gun turning around all the time, then the people in the building nearby will also get a little bit nervous. So you can't use the real systems in the harbor. You could put them in some kind of training mode, but that is something that we used to do. That will be a safety risk nowadays, because are you sure that everything is turned into a training mode, or did someone forget the gun? Could be. So we are approaching this differently now. And what we do is we replace the subsystems with simulators. These are standalone applications that talk exactly the same protocol as the actual subsystem, but they do not see the real world. They see, through a second network, a simulated world, a virtual world, a gaming world. And in this world, in this gaming world, there are ships, and there are planes, and there are weapon systems, and radar emissions, and everything that the normal system would see in the real world is simulated. This is pretty close to gaming, serious gaming, because it's an actual application and not for fun. And because it's a life and death situation that you're gaming for, I would consider it very serious gaming. It's our security that we're talking about. Okay, so given this setup, the part on the left is the standard normal software. It does totally no clue that it's not running the real subsystems, because the API is identical. So that part is not relevant for the training setting. It's the part on the right that's interesting to examine how that's done. And one would think that with a niche market like the Navy, the military, that this is some proprietary setup, but it actually is not. It's based on an open standard, and it was invented in 1993. It's called DIS, or Distributed Interactive Simulation. And there are some issues with it, which I'll get to in the next slide. So it was followed up by HLA in 1996. HLA stands for High Level Architecture. Brilliant name, no clue what it's about. And this is used to create the simulated world. Now, comparing these two standards, then the first one, DIS, was defined by IEEE, American Institute, 1278, and it defines the messages that can be exchanged between the participants in this simulated world. It defines the format, it defines the content, and it's aimed specifically for the military. So the messages recognize an aircraft and a surface or subsurface vessel. And there are fire and detonation events that are being communicated between the participants on the network. But it also has a few assumptions that are a drawback. For example, it uses broadcast for its messaging. And that means that you pretty much flush the network quickly. So scaling this up is a little bit of an issue. And it's only for the military. The messages and the format is specifically defined for the military. So you can't use it for anything else. So the follow-up, HLA, is also IEEE standard, a little bit newer. You can see how many standards they did in those 3 years. Interesting. And it does not define the message, it defines the API. It tells you how to communicate with the network, what the API is, but it does not define how to transport the messages. You can use whatever you like to improve on the broadcasting issue that this standard has. It also is multi-purpose. That means that the messages that are being exchanged over this network are not predefined. You have a model, a federation object model, a FOM, which holds the actual definitions of what's being exchanged and what format and bytes and all this stuff over this network. And that means that you can use it for other things. We'll come back to that later, but you could use it to simulate electric networks or traffic flow. And they added another feature, and that's the concept of a central message bus. So it doesn't define how you're going to transmit the messages, but it does define that the message bus needs to have certain functionality. And one of the key aspects is that it can be time managed. This is optional, but you can manage the way the time flows in this simulated world. We get back to that later as well. And as I said, there's an open source implementation of this. It's called Portico. It's written in Java, and you can download it from GitHub. So if we take a look at this simulated world with the HLA, the RTI as the network message bus, then the participants of such a network, of such a simulated world, are called federates. So we have our subsystems, and they are attached to that world, so each subsystem is a federate and participates in the world. And it, for example, can see another federate that is simulating a ship somewhere in the vicinity. So what would happen? The simulator for the ship will tell on the network, here I am, and our simulated radar will see that and say, okay, well, this is within range, and there isn't any mountain in between, and I don't have interference, so yeah, I'll see this ship. It could cheat, of course, and see everything in the world, but the thing of simulation is that it behaves naturally, so it will take all kinds of restrictions into consideration. So it will see the ship, and it will put a track on the tactical system, and then the operator can decide, well, we're going to engage that ship with a missile, so it will send an instruction. He doesn't know that this is a simulated world, and to the missile system, and it will then fire and create an entity in this simulated world that is a missile. And the missile will transmit its position in the world, and it will use the curvature of the Earth and wind to be as accurate as possible as a missile would fly in the real world. Rain, whatever it needs. If there's fog, then you can't use a optical tracker. It needs to behave as naturally as possible. The missile may then hit the ship. The ship then has to decide if it's damaged and how much it's damaged, what the restrictions are for its operation. It needs to decide for itself what the consequences of a hit would be. There are other entities, federates as well. We could have a plane flying around. We could have a submarine underwater. And of course, we can also have friendly units. There do not need to be enemies everywhere. We can also have friendly units which we can interact with and exchange data with if the simulator allows. And this whole setup can also be connected to another actual real ship that also runs a simulated world. And they exchange the events that happen in their world and train together. This can scale up to fleet level. The Americans even include the Air Force and land-based units. This can really scale up to very large numbers if the network setting allows for such big structure. The whole environment, all the federates participating over multiple networks, is called a federation. So, this is quite a bit of software that we're running here. All these simulators are individual applications, and you need to write them. Now, because it's a standard, then there are also companies that implement this standard for you. And the whole stuff on the right, all these units that participate in the world are written by a company, an American company, original Swedish, but nowadays in America, using a product via Forces. And this provides planes, missiles, ships, submarines, whatever you have in your world as simulators for your subsystems to look against and to train against. Via Forces is something you buy. The subsystem simulators is something that we write. Okay. What I'm going to show you now is I'm going to show you how to start a world and then put a little plane in this world. And for that I need to switch my laptop to the other software, and it's taxed to the max, so it takes a little bit to switch every time. So we have got VR forces here. I've loaded a little map. Can zoom a little bit more. And it's a little map with a small protrusion of a landmass with a little town that we see on top. And what I'm going to do is I'm going to put a little plane here. And for that, I'm going to select over here the simulation. And these are all these simulators that are being provided by the software. I'm going to take A10. It's a plane. I'm going to place it here just off the shore. And we're going to place some additional symbols. We're going to place a waypoint over here, because if we want the plane to do something, then we need it to give it some instructions, and having some waypoints will help it. So we have the plane here. Let me select it and assign it a plan. And in the plan, we're going to give it a task to fly a waiting pattern, a loitering pattern, around the waypoint we just created, gate waypoint 1. And we would like to do it in a tight turn of 500 meters at an altitude of 2,000 meters. And we want it to fly a circular track. That will be okay. Okay, so we've assigned the plane a task, and we can now start the scenario. And if everything goes as planned, no, I don't want to save this, then the simulator has decided that it needs to have some intermediate points in order to get to the track. It will fly there. It will climb a little bit. You see the information here. It will speed up. And then it will enter the track, the circular pattern. And what you see is that the simulator tries to be natural, so it will overshoot a bit and then try to get on the track. It will also, if you zoom in, it will wobble, and it will wobble a little bit to this like a normal plane would. We can also have a 3D view of the plane, and that takes even a bit more of my small laptop. Yeah, now we need to switch, and then the window will be back. Make it a little bit bigger. I'm going to zoom out a bit. It's in a steep turn. Okay. So we now have a world where a plane is flying around. It's visualized here on our display, but underneath there is this message bus, this RTI, which keeps sending and receiving events about, I'm here and I'm doing this and I'm emitting, I've got my radar on you, I've got a radar emission going on. So this RTI with the world is now being populated with all kinds of information. There I am. So the interesting part now, of course, is how do we interact as Java coders with that world? And that is not too complex. This is the scaffolding code that you need to connect to a RTI. What you see on top is that there is a ambassador being created, an RTI ambassador. And the RTI ambassador is used to talk to the I, to tell it what you are doing. There also is a federate ambassador, which is used to listen to the RTI. And in this implementation is the null ambassador, so every method has an empty implementation. And then we create the actual connection. That's the network connection, and then we need to also participate in this federation, and this federation has this federation object model. And in this case, it loads on the top right, the Mac Ripper RPI form, and that's exactly the same form as normally on the disk would be used, so the two standards are interchangeable. If you use the Ripper form, then you can exchange messages between the two standards. And there are some extensions that Mac created for themselves with all kinds of additional functionality. So these green blocks is the object model that's being used on the RTI. And that's it. Now you have a connection. Then you need to disconnect and clean up stuff what you've created, and that's it. This, of course, is nice, but it doesn't do anything. but at least shows the scaffolding. I'm going to hide that away in the following examples. And we're going to try and see if we can listen to that plane flying around. And for that, we need to look into the Ripper form, this object model. It's an XML document. And in that XML document, you see classes like you would in Java, single inheritance being defined. There is the HLA object root. There is a base entity, which is extending the object root. There are many more. I've made a selection. Then we have the physical entity, and we have a platform, and in the end, there is an aircraft class. So our aircraft is of the type aircraft class. And there is an attribute called spatial, and that defines the position of something in the world. So in order to access that information from the plane flying around, we need to change our code a little bit. And we need, so I can read it here. We need to override a method in this null ambassador, and that's the one that is being called when a value changes. And we need to start listening to the plane information. Now for that you see that the pattern of classes we just saw in the Ripper form is present in a dot notation here. And we're going to listen to everything of the type aircraft class. So not a specific plane, every aircraft we're going to get information about. And we're going to listen to the spatial attribute of that class. And when we see it, we're going to print on top, we've got a new spatial information of a aircraft. But of course, you would like to see what's in the spatial information. Now, Ripper form also has all kinds of type definitions. Spatial is of type spatial struct, and it has, depending on some enumeration, a certain structure, which has a world location, and the world location is XYZ. And XYZ, in the end, is a 64-bit big endian float. We're talking about the 90s, we're at bit level here. And this whole structure, complex as it is, you can pretty much one-on-one mirror into Java code. The block on top is where you get the types and then can put the bytes in it and get the information out. So how would that look if we would run that code against our example? And I'm going to switch again. The plane is still flying around. So this is the actual code. Here you see the connect statement. You see the decode and print of the spatial information using all the byte structure over here when it's listening to the method. And here you have the class definition and listening to the spatial attribute. And the main thread doesn't do anything except sleep for a bit. So if we start this example, it's now loaded the connection information, and then it prints the XYZ coordinates of the plane flying around. And you can see that the Z changes as well, so the plane isn't all stable. It wobbles a bit as it would in real life because of wind and all kinds of factors. So it flies around, and we get its information. But that's all nice. We've got a Hello World application, connecting to it, printing something. It will be more interesting if we can also interact with it and have something appear in this world. And for that, I need to explain a little bit. So we have this class diagram, and the lowest class is an aircraft, but we've got an A-10 flying around. And that's a specific aircraft, not just any aircraft. And for that, the structure has a field called entity type. They didn't define every possible military asset in the FOM model, because that would require a lot of changes if something new comes in. So they have an attribute value for that, and the attribute value entity type is part of a very long list of almost 800 pages of just numbers. And it specifies what type of aircraft or plane or tank or whatever it is. This can be easily extended and removed. There are hardware things that are no longer used, the Grumman in the middle. And for our example, I would like to introduce a C-130. This notation, it kind of resembles an IP address, only with 7 positions instead of 4. Can be very specific, so I can use the long notation, then I have a C-130. I can make it even longer and denote a specific aircraft or a specific ship. There is a number in this list for the USS Ronald Reagan aircraft carrier, for example. Or I can make it shorter, and it will be a more generic identification of the entity type that's flying around. And what you need to do then is you need to create an instance of the aircraft class we just created. That's done here. And then you need to assign this number, this IP-alike number, to the aircraft, and that will give it a certain type. What we'll also do is we'll save the position information of the A-10 flying around to make it simple. So we store it into a local instance variable, and then use that to give our C-130 a position in the world. Because this XYZ is a complex structure, and having code for that would make it easier. So this will cause the C-130 to follow the A-10 around. Let's see if that indeed works as we hope it to. So here we have the code again. Let me see, the interesting part is the assigning of the spatial value to the plane. That's this line. So we're going to start this code. Let me see, the shadow plane, run. And then we're going to switch to the 3D view and hope that the demo effect will not kick in. There the plane is coming on the left. You see it here, the C-130, and there it is. And it's following the plane. Now, theoretically, the simulator could have reacted to this and could have detected a collision. It doesn't. It reacts to a fire and detonation event, the simulator, so this doesn't cause a collision, but you could have implemented it in this way. And the asynchronicity has to do with the sleep statement and when the event comes in, so when sometimes it's pretty close by and something it's lagging a bit behind. Okay. See how much time I have? Yes, on track. So it's not that difficult. The pain is always in the detail, but it's not that difficult to do. If we take this setup we've just written, we've created our own plane on the right side just now. But if we take a step back and not look at the specifics of the implementation that we're doing, then we have a message bus. And on this message bus, there are some independent applications. They all do their thing, they exchange messages, they're reacting to events, and they all have their own state. They have their own damage state, they have where I'm at, and they just communicate with each other what they're doing. Basically, these are microservices. Invented in the 90s, but the concept is not that new. Stateful, you can't load balance them, but nevertheless. The only difference is that they can be time managed. And this time managed is what makes this simulation interesting. For training, we need to be real time because there are people behind it. But for other usages, it can be very interesting to use this time managed aspect. The code we just saw isn't time managed, it's real time code. And what does this mean, being time managed? My table is coming apart. Okay. So take, for example, we've got 3 federates, a submarine, a ship, and a plane. And the RTI, in time managed mode, will ask everyone, what are you doing? And the submarine will say, yeah, well, I'm at the bottom of the ocean here, and everything is peachy. I'm blowing my bubbles, and I've got nothing to do for the next 10 seconds. Okay. And then the RTI asks the ship, and the ship says, well, I'm sailing along, and I intend to make a turn in about 5 seconds. But everything is okay with me. And the plane, in the cartoons, they're always very active, says, well, I'm a bit faster. I have to update my position in 100 milliseconds. So the RTI says, okay, that's good. And it moves the time ahead 100 milliseconds and allows the plane simulator to transmit its position. Great. And then it starts again. Okay, who's intending to do something next? And the submarine is still bubbly, the boat is still sailing, and the plane says, yes, in 1 second I intend to do something. So the time moves ahead to 1 second, and at that point the plane decides to drop a sonar buoy in the water. Boom, and it does a ping. So at that point the event on the world is a ping event, which causes the submarine to change its mind. It says, okay, I've been pinged, I'm not going to wait anymore, I'm going to move. So it changes its decision to not do anything for 10 seconds to, I'm going to react to whatever happened in the world. And the time will move ahead to that position. You don't need to actually wait the amount of time. It's just a measure of synchronization. If no one intends to do something for 10 seconds, then you don't need to wait 10 seconds. You can just jump ahead and then decide, okay, we're now 10 seconds further. What are you doing now? So this time management makes it possible to have time move faster than real time or slower than real time if you're doing complex calculations and you're not done within the second that you said you were going to do something. This faster than real time allows for calculating through all kinds of scenarios and settings in quicker than what you normally would have to do. So to summarize, we've got an open standard and open source implementation for doing simulations. And it can be used for the military, that's where it was invented for, but the HLA also allows it to be used for other domains. And you could use it, for example, to mimic a complex traffic situation, where you have car simulators and you have lanes, and you have a natural behavior of the cars, and then see how they get through the traffic situation. Or you could simulate electric networks, have electricity systems, have cars plugging in, and then see how the network would behave if there were normal interactions with the electric network. Or, for example, a train system. Suppose you have a certain setup in your in the position where your trains are, and then you have a certain schedule, and then you can start calculating, will this new schedule cause any conflicts? Trains behaving naturally, having stop time at stations, and all kinds of things. So this time management aspect is a key feature compared to the normal networking. It allows you to have a natural calculation of whatever would happen in your setting, in your scenario, faster than having it run at normal speed. It's available for C++ and Java, and it will work nicely with containers and Kubernetes, what we use nowadays. It's just a network bus with applications coming up and connecting to it. So there's no reason why we can't use modern infrastructure to use this 25-year-old standard. Okay. So I'm pretty on schedule. Are there any questions?
So since this is the military, I would assume that you want some of this information not to fall in the hands of, for instance, Russia or China, but still it's open source. So are there parts of it that are not, or how do you?
No, so the question is, should we have this secured and not in the hands of China or Russia? Well, the network and the protocol itself are not that special. It's just a standard. The algorithms inside the simulators are something that are restricted. And then the stuff that the MAC, the VR forces provide, is also not that special, but the stuff that we write ourselves, those can't get into the wrong hands. Yeah.
Do you have a separate setup with a closed room so that they could
So every workstation, every mock can be switched to training mode. The F126 will have 2 simulated worlds, and they can select the workstation to be in the real world, or in training world 1, or in training world 2, and they can even train against each other, having a set of mocks in the one world, a set of mocks in the other, and then pretend to be 2 different ships, and practice with or against each other. And that's just how you want to do it.
Maybe a bit unrelated, but just curious, do you happen to know if these simulations are also used, for example, for self-learning AI and self-driving cars? That they target a simulated world rather than having them actually drive around?
Good question. If this is used for the new self-driving cars, I don't know if this is being used. It would make sense because it's working. It's a standard. I would assume that they could, but I don't know. I don't know.
You showed the electricity and the car networks as examples. Is it used by the Dutch railway systems?
I sat with them at dinner yesterday, and I proposed it to them, and they started thinking. Yeah, that's a very good question. Can you fool the real system with fake events? Yes, you can. So it would be possible to introduce these simulators onto the real network. If I would replace the API of the subsystem with a simulator in the real world, it would inject the events and the operator wouldn't know. So this is a security feature, a safety feature that we need to prevent. That you can't, we have network separation, and you can't access the simulators from the operational network. If bad guys get access to the internal network of the ship, then that would be a problem, yes. But they're not supposed to. We will try to prevent that. Yeah, okay, so it's all shielded, and so there are measures in place to prevent that. But yeah, that would be a problem. Any more questions? No? Okay. I've got 3 minutes, so I've got a question for you. Is it a boat or a ship? It's one of the interesting topics that I pondered about when I first joined Thales 3 years ago. We've got a boat and we've got a ship. What defines when something is a boat or a ship? And there are a number of definitions possible. The one I like most, there's no official situation, but the one I like most is this one. Can you guess? The right one is a speedboat, the left one is a ship, a navy ship, but what is the difference?
Staying dry or getting wet?
If you have a fancy speedboat, then you would stay dry as well. Now look at the inclination. A boat leans into a turn, speedboat leans into the turn, and a ship leans outward when it makes a turn. It's a definition that I found somewhere. I like it. Other ones are that you can put a boat on a ship, but a ship not on a boat. And of course, it has to do with the level of gravity and that the inertia point is higher above. But I like this definition. So, okay. Thank you for your attention, and we're exactly on time. So have a good day.